I'm Janice Shaw, president of AMSA Incorporated. This video will show the importance of using AMSA BCP chemistry in regular maintenance water treatment programs. I'll talk about how to use the chemistry to achieve different outcomes in both performance and economics. This is a picture of fouled systems that have been cleaned by AMSA BC chemistry over the years. However, you don't have to have this level of fouling in a cooling water system to have negative impacts on that system. Let's talk about some of the different ways that biofilm contributes to negative impacts in cooling water systems. And biofilms certainly do contribute to corrosion. This is a picture of corrosion on the tube sheet of a heat exchanger. You can see the pitting into the metal, and this was caused by acids concentrating under a biofilm deposit and eating away at the metal below it. Let's talk about biofilm's contribution to scaling. While you may be familiar with the fact that biofilm does contribute to corrosion, you may not be as familiar with the fact that biofilm can cause scaling. This is a picture of scaling in a cooling water system. Biofilm bacteria forms a substance called EPS, or extracellular polymeric substance. EPS attracts minerals, in particular calcium and magnesium. When these minerals concentrate in a biofilm deposit, it can initiate scaling, and this is especially true in heat exchangers. So let's talk about biofilm's effect on heat exchange. This is a picture of slime on the tube sheet of a heat exchanger. The first illustration next to this picture shows how a heat exchanger tube works to take heat out of a service fluid in a cooling water system. In the second picture, you can see how a layer of biofilm on either the outer or the inner surface of a heat exchanger tube will greatly impact the thermal conductivity or the heat exchange of that heat exchanger tube. Let's look at thermal conductivity ratings for different metals. As you can see from this chart, copper and aluminum both have very high thermal conductivities, and consequently, both of these metals are often used to construct heat exchangers. When we look at the thermal conductivity of scale and biofilm, you can see that these numbers are much lower. In fact, both scale and biofilm tend to act more like insulators, as you can see from the chart that shows the thermal conductivity ratings for insulating materials such as glass, insulating brick, asbestos, and styrofoam. Between scale and biofilm, you can see that biofilm is the best insulator or the worst at thermal conductivity. This chart shows the loss of heat transfer in relation to greater layers or thicknesses of both calcium carbonate and biofilm. The blue line shows that at zero point 0.2 millimeters of scale thickness, there is a loss of nearly 60% of heat transfer. The orange line shows that at that same zero point 0.2 millimeters of thickness, you are looking at a loss of conductive heat transfer nearing 80%. When the thickness of the deposit increases to zero point 0.9 millimeters, the loss of heat transfer for scale is near 80%, and the loss for biofilm is near 90%. Certainly, if your cooling water treatment program is not delivering good biofilm control, your customer's cooling water system is not working efficiently. Let's look at the costs related with not running an efficient cooling water system. This chart was developed by Innovus Technologies. Their calculations were based on a chiller efficiency of 0.61 kilowatt tons, an annual operation of 3,000 hours per year, and energy costs of zero point 0.9 cents per kilowatt hour. You can see that for a chiller with 900 tons of chiller capacity, if a scale deposit thickness of zero point 0.2 millimeters is present, it takes nearly $6,000 of additional energy to deliver the cooling efficiency needed. If there is a deposit thickness of 0.9 millimeters, the cost increased to $40,000. Let's look at that same system now with biofilm deposits. Again, a system that is a chiller capacity of 900 tons. When there is zero point 0.2 millimeters of biofouling thickness, the cost of the energy needed to deliver the cooling is nearly $24,000. When that thickness increases to zero point 0.9 millimeters, it jumps up to nearly $160,000. There is a great cost to facility managers if the cooling water systems are not running efficiently. This chart lists the operational impacts of biological fouling. We've already discussed that biological fouling can greatly reduce heat exchanger efficiency. We've also talked about the fact that biofilm deposits cause microbially influenced corrosion. I'd like to discuss the greater risk for Legionella when there is poor biological control. Legionella is protected by biofilm deposits. When biofilm deposits are allowed to grow to a greater degree in a cooling water system, you have a greater chance of those deposits sloughing off and becoming aerated from the system. When these deposits or when this bacteria pathogens are let into the air, it can cause people to become sick and in some cases to even die. All of the impacts listed here are great concerns to facility managers running cooling water systems. Adding AMSA products to your cooling water treatment program helps you deliver a better biofilm control program. This is true because AMSA products penetrate organic deposits, clean and remove organic deposits from surfaces. When used on a regular basis, AMSA products can help inhibit and prevent deposits from adhering to surfaces. They act as a biocide penetrant aid and help the biocide get into biofilm deposits to kill biofilm bacteria. And in this way, they are synergistic to biocide performance. In this next set of slides, we're going to use a graphic image that AMSA created to show how AMSA products work in a cooling water system. This is the picture of a cross section of a pipe in a cooling water system. The yellow substance at the bottom of the pipe represents a biofilm deposit. The rods represent biofilm bacteria that are located within the biofilm deposit. And you can see below the yellow EPS sugary substance, it is eating away at the metal below it, and that is representing microbially influenced corrosion. While it's not accurate that biofilm deposits all settle in one spot at the bottom of a pipe in a cooling water system, it is accurate that most of the bacteria in the system is located within the biofilm deposit. It is estimated that 90% of bacteria in a cooling water system is indeed in biofilm deposits. So the rod-shaped bacteria that are floating in the bulk water or planktonic bacteria represent just about 10% of the bacteria in a cooling water system. In this picture, the red dots represent the concentration of biocide in that system. As you can see from this picture, biocides tend only to be able to penetrate the outer layers of a biofilm deposit. This is the case for oxidizing biocides as well as for non-oxidizing biocides. While some non-oxidizing biocides do have penetration, it is true that with all biocides, a high concentration of biocide is needed to try to get into the biofilm deposit. This is where AMSA chemistry comes in. In this picture, AMSA chemistry is represented by white dots in the cooling water system. As you can see, the AMSA BCP chemistry does a better job of getting into the biofilm deposit. And this is true because AMSA products have three key modes of action. First, they go to surfaces, and the chemistry readily associates with biofilm deposits. There is a long carbon chain on part of the molecule, which allows AMSA BCP chemistry to deeply penetrate in organic deposits. Once the chemistry is inside of the deposit, there is another portion of BCP chemistry molecules that acts as a chelation function, or it breaks apart the deposit. It is these three key modes of action that make AMSA BCP products very efficient at penetrating, breaking apart, and weakening biofilm deposits. When biofilm deposits are weakened or sloughed off of surfaces, it is much easier for biocides to be able to get inside of the deposit or to surround it and kill the biofilm bacteria, as shown by this picture. So, in this way, a program that has both AMSA BCP chemistry and a biocide is a much better biofilm control program. AMSA BCP products are well known for their ability to clean fouled systems. The pictures on this slide show how, after dosing AMSA products into a cooling water system, usually within 30 minutes, you will see a slurry carrying up entranced biofilm deposits, organic deposits, inorganic deposits, corrosion materials, whatever was entranced in those biofilm deposits. I am not going to focus on how AMSA products clean a cooling water system. Today, I'm going to talk more about how, when you use AMSA products in a regular maintenance program, you can keep cooling water systems clean. There are two types of dosing programs that customers use to keep their systems clean. You can use a slug dose program or a continuous dose program. AMSA products are designed to be used with biocides, so you coordinate the use of AMSA products with a biocide to get your optimal cleaning and to get the maximum effectiveness from the biocide. They are compatible with both oxidizing and non-oxidizing biocides. I'm going to talk about different ways that you can dose AMSA products, and to do that, I am going to use the chart on this slide. The y-axis on this chart represents increasing levels of biofilm and thicker deposits. You can see that it goes from the blue zone, where biocides are effective, there's good heat exchange, the inhibitors are effective, it looks clean. And then as the biofilm deposits become thicker, you start moving into more of a problem zone. And this goes from the orange to the red color. And in this case, you have biocides that can't penetrate the thickened deposits very well. Your inhibitors are not able to reach surfaces. You've got problems with corrosion and scale. Your heat exchange is suffering, and overall, it doesn't look very good. The x-axis on this chart represents time, and in this instance, we're talking about the time period of a year. This graphic is showing a twice-a-year cleaning. In March, a cleanup dose is administered as the cooling season is oncoming to prepare the system for the summer months. Then, as the weather heats up, the bugs start to grow more. This system starts working in the problem zone. More biocides are needed to keep the microbiological fouling in control. Inhibitors are not able to reach the surface. You can see over the months of May through November, this system's pretty much working in the problem zone. And there are a high level of costs for chemicals as well as energy needed to deliver the cooling required from this cooling water system. Then, after the cooling season, as the temperatures start to get cooler, a cleanup dose is administered to prepare it for the winter months. I would argue this is not the best way to run a cooling water system. It is far better to use a treatment program that has a regular cleaning regimen. So, in this instance, the x axis changes to a weekly time period. And there are slug doses of AMSA BC chemistry administered throughout the week. On Monday, there is a cleaning dose. And then on Tuesday, you can see that after the system is cleaned, Bacteria starts to grow. Slowly, the biofilm deposits increase in size and in quantity. And then on Wednesday, another cleaning dose is administered and the system is cleaned once again. Over the period of a day, those deposits start to grow back. On Friday, another dose is administered. Over the weekend, there's an extra day, and so the deposits become thick enough to start causing more of those operational problems we've talked about in an earlier slide. But then again, on Monday, a dose is administered and the system is cleaned again. This sawtooth pattern of cleaning, allowing the system to refoul to an acceptable rate, but then cleaning it again, allowing it to refoul, and before it gets into too much of the problem zone, cleaning it again. This cleaning, refouling sawtooth pattern is that of a slug dose maintenance cleaning program. How often you dose and at what concentration is determined by the refouling rate of the system. In some systems, a cleaning dose of 3 times a week may be appropriate. In other systems, if the refouling rate is not that fast, you may only need to dose it once a week. In some systems, you may only have to dose it every other week. If you have a system with a more aggressive refouling rate, you might have to dose every day and at a higher concentration. The concentration of the chemistry and the frequency of the cleaning are all dependent on the refouling rate of the system and how clean the system needs to be. For example, an industrial system may not need to be cleaned at the same level as a system such as a hospital, where the concern of pathogens and Legionella may be much more acute. Some considerations to consider when thinking about using a slug dose program: consider the system refouling rate. What is that level of cleanliness that's required for the system? You need to think about the conditions of the surrounding environment. During certain parts of the year, there is not a lot of organic material that would be introduced into the system. But when you have the season where possibly pollen is floating in the air and being sucked into the cooling tower, there will be a higher organic load, and you may need to dose at a higher concentration or more frequently. If a cooling tower is located near a agricultural lot or maybe a sausage factory, again, you may have more organics in the air sucked into the cooling tower, which would require a greater frequency and concentration of chemistry. So let's look at what a slug dose program looks like for AMSA BCP 1015 or BCP 2175. They tend to be dosed at a rate of 25 to 65 ppm of product, and that is based on volume. A regular program could be 1 to 3 times per week, but again, both of these are dependent on the target level of cleanliness as well as the system refouling rate. Best practice is to feed AMSA chemistry before a biocide slug. When you think about how the chemistry works, go back to those graphics that we went through. The goal is to have the chemistry in the system for maybe 2 to 3 circulations, giving it time to soak into the deposits, to open them up before you introduce a biocide slug, which is designed to disinfect and kill the bacteria. And it's important that you monitor your system quality control measurements to ensure that the concentration and frequency are keeping that system to the level of cleanliness that you desire. This chart represents a continuous dose program of BCP products. In this scenario, you are keeping a low level of AMSA chemistry in the system so that it is continuously cleaning surfaces. In this way, the biofouling deposits are kept to a minimal level. And in turn, that system is able to have good heat exchange. It allows the biocides to work at their maximal effectiveness at their lower levels allowed on biocide labels. Inhibitor chemistries are effective, and the system looks good. This type of system is recommended when you need a high level of cleanliness, such as in data centers or hospitals or assisted living facilities. And in this type of a program, you're dosing AMSA chemistry, BCP 1015 or BCP 2175, at a low rate. That would be somewhere in the area of 2 to 10 ppm of product. Now, note this dosing is based on blowdown. And once again, the product concentration depends on the regrowth rate as well as the acceptable level of cleanliness for the system. Because you're dosing the chemistry continuously, you do not have to factor in the frequency of the dosing program. BCP 6010 is a product that AMSA has developed to be a continuous dose product. BCP 6010 is dosed at 50 to 150 ppm, and that is more on par with the dosing levels that you use with your inhibitor chemicals. It is based on blowdown. Once again, the concentration depends on the microbial refouling rate as well as the level of cleanliness that is acceptable for the system. BCP 6010 was designed in particular to be used with a continuous oxidizing biocide program. It easily integrates into your current treatment program because it is dosed at a rate that is similar to inhibitor chemicals. You can tie it to the controller for your inhibitor chemicals. It provides consistent cleaning performance. Again, in this way, it limits the establishment of Legionella and reduces the risk of having a Legionella outbreak or getting high Legionella counts in your cooling water system. It is very substantive to surfaces. And because you're keeping a low level of AMSA product in the system at all times, you will get the best boost from the properties of the chemistry that are film forming. AMSA chemistry has a natural tendency to form a film on surfaces, and when it is not being used to clean deposits, it protects those surfaces. It has an azole like property. And again, when the system is kept to a very high level of clean and there are low levels of biofilm deposits in the system, you're not allowing them to regrow to the rate where it needs to be cleaned on a regular basis. You get the best bump from that film forming characteristic of the product. When dosing AMSA BCP chemistry, consider what is the system size? What is the recirculation rate of the system? Again, thinking to get 2 to 3 circulations of the chemistry through the system in order to soak into the biofilm deposits and allow the action of biocide to be more effective. How fouled is the system? In this instance, you may need to use a higher concentration of chemistry to clean the system, or you may be concerned that if the system is highly fouled, you will be breaking loose a lot of deposit. So you might actually want to decrease or back down on the concentration of the chemistry so that you are more controlled in releasing deposits from the system and allow your bleed and your filtration to remove the deposits. And in that way, take a longer time to actually clean the system, but do it in a more controlled manner. Also note, are there areas of high agitation? We know that foaming occurs when you have high levels of organics as well as mechanical mixing of air into the system or into the water. So, in this case, if you have a high level of agitation, you may be concerned that you will generate more slurry or more foam, and in this instance, cut back the concentration of chemistry. Another consideration is, where are you dosing? If you're concerned that most of the biofilm deposits are forming in the fill, you may choose to dose closer to the cooling tower fill so that the highest level of concentration of the chemistry is introduced into the system right before the fill. If your concern is with the heat exchanger, you may wish to dose closer to the heat exchanger if you have that opportunity. And finally, how clean do you need the system? Whether you use a slug dose or a continuous dose system really depends on the level of cleanliness you need in the system. Let's take a couple examples of cooling water systems and look at the amount of chemistry needed for different types of dosing programs. This is a graphic of a typical cooling water system. Let's look at a slug dose program with AMSA BCP 1015 or 2175. The system volume of this system is 10,000 gallons of water. The blowdown, 289 gallons per hour, and the holding time index, 24 hours. If you have a slug dose program that is 3 times a week at 45 ppm, you would be looking at using 1.35 gallons of BCP product per week. Now let's look at that same system as a continuous dose program with BCP 6010. In this instance, we would use the lower range of concentration or 50 ppm as you are keeping surfaces continuously clean. At that level, you would use 2.4 gallons of BCP 6010 per week in this system. We know that your economics are all different for different systems. The types of programs that you need, the raw materials for the amounts of chemistry that you use at that system are all varied. So AMSA has developed a new biofilm control program calculator. In this calculator, you can list the BCP product that you would like to use. You can choose either a continuous or a slug dose program. You can input the frequency of dosing as well as the concentration. It will then calculate your cost per week. You can add an oxidizing biocide, again, the type of program and the cost for that biocide. You could add a non-oxidizing program. And then the calculator will automatically calculate the costs for that entire program for week and per year. This slide shows the QR code to go to that calculator as well as the website address. And you can see there's a picture of what the calculator looks like. I would argue that keeping a system clean pays off. When you have biofouling deposits that are cutting back your level of heat exchange, the energy cost to deliver the cooling needed does add up. And once you corrode metal, you can't get it back. It costs a lot of money to retube a heat exchanger. And if you're allowing high levels of corrosion, your system lifetime will definitely be shorter. If you have to replace cooling tower fill, it's expensive. And higher biocide and inhibitor costs will be needed to keep up system performance if you allow a high level of fouling. Finally, I'd like to talk about maintenance for small cooling towers. AMSA has developed a product in the 3000 series, and there are actually two products, DTA2 SR and DTA2 SR plus SC. These tablets are designed to deliver AMSA chemistry in a solid, slow-release form. These tablets are designed to have a lifetime of 3 to 4 weeks, so you can use them with a monthly service visit. One tablet, the SR, has just AMSA cleaning chemistry. The SR plus SC has added chemicals so that the tablet can provide AMSA chemistry as well as scale and corrosion control for small cooling towers for up to a month. These are excellent solutions for maintaining clean and good corrosion and scale control in small cooling towers. As these pictures of lawn cutting indicate, it is much better to keep systems in control than deal with them once they are out of control. Thank you for listening to this video presentation. If you have any application questions about using AMSA BCP products or you would like to get a quote, please contact me at janice@amsainc.com or call us at 989-662-0377.